Today we're going to be looking at standardizing the normal distribution that we looked at last week with the normal bell curve. And we had, 1, 2, and 3 standard deviations away from the mean, which is in the middle. And we talked about the empirical rule where we had 68%, 95%, and 99.7% of the data in between those standard deviations. Well, we can also take and talk about a normal curve, normal standard curve, such that the mean has a standard deviation of 0, and then we would have a +1, +2, +3, a -1, a -2, and a -3. So rather than actually assigning that value where we took the mean and added or subtracted the standard deviation, we can just talk about it in terms of a measure of standard deviation, and we'll also include these decimals in between 1, 2, and 3 standard deviations. So a z-score or a standard score is just, again, a comparison between the data value and the mean of the data set. And so this helps us when we're comparing two data sets that don't have the same mean and the same standard deviation, but we want to compare two data points in two different sets because it's standardizing that number, and so then I can actually compare one z-score to another. So an example would be if you wanted to compare how a student did on test 1 versus test 2, they're going to have different class averages and standard deviations, but if we find the z-score, then we can say, well, on this one they were 1.25 standard deviations above the mean, and this one they were 0.75 below the mean, and so test 2 would have been not as good as test 1. The formula to find a z-score is to take the data value, which we represent with x, subtract the mean, which we represent with mu, and divide by the standard deviation, which is represented there by sigma. And so because I'm taking the distance away and then dividing it by the standard deviation, I'm taking that distance and breaking it into the same number of chunks, and that's how we end up with some z-scores that are not whole integer numbers. So when you get those z-scores, you do want to make sure, because they are decimals, that you round to the nearest hundredth. I'm going to show you how to use your calculators if you have a calculator when we're on one of our meetings this week. If you don't have a calculator, you can still find the z-scores and the percentiles, which is the area under that normal curve, using a table, but you're going to need your z-score to the hundredth to be able to use that table. So it's just kind of a good habit to get into as we start looking and calculating z-scores. So again, data value, subtract the mean, so you find the distance between the two values, and then we take it and divide by the standard deviation so that we're breaking up into the same chunk of distance. So how we would use this, so the points Vicky scored in basketball games this year are normally distributed. So again, we do need to know it's a normal distribution to use this particular z-score, with a mean of 18 and a standard deviation of 4. And so then we can calculate these 3 different z-scores. So for 5 points, we would take the value 5, subtract the mean of 18, divide it by the standard deviation of 4, and we get a z-score of negative 3.25. And so the way we interpret that score is that her gain with 5 points is 3.25 standard deviations below the mean. And so if it's below, obviously she didn't score as well in that game. Versus a game where she scored 21 points, we would take 21, subtract 18, and divide by 4. We get a z-score of 0.075, meaning that she was 0.75 standard deviations above the mean. So she was really close to the average in her score for that game. And then the last one is for a score of 12 points. So 12 minus 18 divided by 4 gives us a z-score of negative 1.75. Again, we're in the negative, meaning that we're below the mean. So the game where she scored 11 points is 1.5 standard deviations below the mean. And so because, again, we have these positives and negatives and the mean, and that just kind of gives us a visual once we understand what the bell curve looks like about how far away we are from that average. And we know from what we looked at last week that, 1 and 2 standard deviations, 68% of your data should be there. 2 and 3 away is kind of the far distance, I guess, from the average. We're kind of getting further away from the average there. You can also find a z-score if you're not given the mean and the standard deviation. You just have to find those yourselves. So you would take the data set and find your average and then find your standard deviation. Now you should hopefully be using a calculator to do that. If you have a TI-84 calculator, when you pull up and calculate the average and the standard deviation, what you want to pay attention to is the fourth and fifth line down. So you see SX and you see sigma X, and they're two different numbers. Those are both standard deviations for that data set. What the calculator doesn't know when you type all of that in is whether you're giving it a sample or a population. And so for this one, we're going to assume that it's a sample if they don't tell us otherwise. And so we would use SX. If you did know that you had a population, you could use the sigma X because you would have to, don't have as much error there basically because you know that you have the entire data set. So again, mean and standard deviations, so we want to compare these three scores, a 64, a 76, and then a 102 to see where they fall in comparison to the average or the mean. So for 64%, 64, subtract the 81.2, which was the average, divide by the standard deviation. It's going to have a negative 1.25 as a z-score. For 76, 76 right away, I should be able to look at that and say, well, I know that 76 is below the mean, so I should have a negative z-score. It's not going to be a huge z-score because 76 is relatively close to the mean when you compare to that standard deviation of 13.8. So that would have a negative z-score of negative 3.8. They're not even getting to that, the one standard deviation away. And the last one would be a score of 102, so somebody that scored above a perfect score. And in that case, it's going to be 1.5 standard deviations above, and it's positive because 102 is greater than the average. And again, knowing what we know about standard deviations, 1.5 is actually a good distance away from the mean, above the mean. It's going to be unusual to have somebody to score above a 100% on an exam. So again, just a way to kind of compare and see what it is that we're looking at, and a way to standardize our thinking around these points. So again, talking about being able to make comparisons. So we have the z-score of 4 students on the math test. We know that the mean was 87, a standard deviation of 5.1. So we're actually going to work backwards to find the test grade or the score that the student got on the test. So we're going to use the exact same formula: score, subtract the mean, divide by the standard deviation, and then we're going to make it equal to the z-score. So rather than plugging in for our data point, we're actually going to plug in for the z-score and work backwards. So for Matthew, we would take his score, 1.3 equals x minus 87, divide by 5.1. When we solve that algebraically, we would see that he scored a 93.63. Ryan's z-score is a negative 0.02, so I know right away that he scored less than Matthew, and it should be probably quite a bit less than Matthew. So let's see. Not quite a bit. This actually has a smaller standard deviation than I think what I paid attention to, but we take his z-score, set it equal to the formula, solve the formula. He's going to have an 85.98. Tammy probably didn't do as well. So Tammy, once we take and calculate and work backwards, she would have a 70. Bill has a 2.67, meaning he should have scored above where Matthew scored. And again, that's almost 3 standard deviations away. We have almost no data points that far out away from the mean. So once we plug in and calculate for Bill, we see that he would have scored just over 100. So he probably got a perfect score on that test. So again, it's really just a way for you to kind of make comparisons without knowing specific values within the data set.